Hello and welcome back to Information Storage and Retrieval. Our information retrieval system assignments continue. So, last assignment, we were working on getting queries to populate, right? So we were trying to say we've taken an index that we've built, and now it's time to see what the user can do, right? We want to enable them to do a search. That's kind of the whole point. So, would you, for example, last time we got to the point of we tokenized, carefully changed the text. So if we do would you, right. We do all the stripping, the cleaning, the getting rid of all the extraneous stuff, and we turn them into tokens, right? The same kinds of tokens that we would normally use in our index, right? So the terms. So let me go back to the top, would and you, right? And using those, we would then say, okay, so what are the postings for would? Where does would live in our collection? So in this case, in our little green eggs and ham snippet, would appears on lines 0, 3, 4, and 5. Would, and would. Got it. Then we also have you, so this is the other set of query postings, 0 and 3, great. So that appears in, I jumped to the postings. Right, so 0, that's the first line, and 3, that's the fourth line. So would and you, being the two tokens that we're looking for, we want to return just 0 and 3. But remember, to do that, we have to jump through the hoops of doing an intersection algorithm. In fact, the one we talked about in lecture. While you could certainly do this on your own, I feel that not do it on your own, but you could easily look up a set of functions for doing set stuff like intersections and unions and all that kind of stuff. Totally valid to do that, but because we've talked about the algorithm for intersections at length in the course, I think we're going to do it. We're going to implement it from scratch. So, adjusting something over here. So let's look at what we're going to do today to get from these basic query postings that show, okay, so here's the would postings and the you postings. How do we get from there all the way to our proper search results, right? So our results have kind of come out the other side, right? So we've got documents that went in, a collection is in our internal data structure of that. We have our index and we have our query and we have some unranked results at the end. So what are the steps? Well, we need to sort these query postings, first of all, to prepare them to do the intersection algorithm efficiently. Now, if you remember, the intersection algorithm, if it reaches the end of a list doing all of its comparisons, and then it falls off the end of it, we know that we're done. That's why we want to be able to do this one first. So we sort them so that this will be the first, the U ends up being the first one processed, the U postings. And then would ends up being the second one processed. And in this case, there's only two postings, so it doesn't really matter. But if we wanted to do would you like, right? So if we look at like has lots of postings. In fact, I think it's in every line of this book, 0, 1, 2, 3, 4, and 5, right? So we wouldn't want to process like early, right? We want that one to come last if possible because it's in every line. I mean, in most cases, you would try to just throw that term out anyway because it's totally useless. But the idea being that by the time we get to processing, if we've done like first and we're doing an intersection, then the interim results can't be any larger than our smallest list. So we'll do like with would, and then we'll do whatever results from like and would with, sorry, not like. We'll do you and would, and then like comes last, and thankfully the interim results will be very small. This should just be ringing some bells for you. I know it's not terribly easy to follow along without strict visuals, but remember the idea of that algorithm. The idea is we're going to run through 2 lists at the same time. We're going to say, okay, from 0, we're going to see, is 0 in both lists? Good. We'll hang on to 0. We'll then both move them along. Is 3 in both lists? Great. We'll move on from 3. So now 0 and 3 are in our list. And then 4 and 5, oops, we're out of stuff in our first set. So now 4 and 5 can't possibly be in our results. We'll get to this. Look back at the lecture if this is not ringing bells. Remember, we had the whole description of the intersection algorithm to follow along with. So if you're getting a little twisted, use that. So from there, the idea is no matter how many terms we have in our search, right, in our query, we want to run through and do an intersection on each list of postings at a time. So we do the first 2 in order of smallest to largest. Then we do the next one with that interim result, then the next one with that interim result, until we narrow everything down to a list of postings. The list of postings being the intersection among all of the tokens that were included in the query. Looks like only documents 0 and 3 have all 3 words, would you like, because we've done this intersection algorithm. So, would you like shows up in documents 0 and 3. We can manually check this. 0 would be the very first one, so would you like? Great. And then does not happen. 3 would be the 4th one. Would you like? Hey! So, that's what our result is. We have walked through the process of converting a user query into the same language as the index, getting all the postings numerically out, arranging them a little bit ahead of time so that we can do our intersection algorithm efficiently, and then bam, do the intersection. Now, on the front end here that we're seeing, there's very little, it looks like this is a very small step, right? Between, oh, the sorted postings suddenly become the intersected postings. Great. That's actually most of the work of this one. So you'll see there are actually 2 functions we have to use to have to implement to make this work. So, yeah, so that's the idea. This is what we have here. I guess I can show, is that right? I can show the intersection concept at play. So intersect, if we're going to have, let's say we're just trying to do any old intersection. So 1, 3, 5, and 9, right? And then 2, 3, 7, and 9. Now think about this. Remember, I just spoiled it with the autocomplete. But that's the idea, right? So we're going to have to implement this algorithm that says, okay, here are a list of values, another list of values, and I'm going to find which ones are common among those lists, right? Intersection. This is what we'll do to each set of query postings, and until we run dry, right? Until we either run out or we have a small reduced set. So, how do we do this? Well, let's have a look at the code for this page, as we always do. I'm gonna make it, let me shrink this one. Get rid of that. And give a little more space. Okay. As usual, we've got lots of boxes. We've added some since last time. I think last time we ended at query postings, right? So that takes us to query postings. We've now added the query postings sorted box, query postings intersected box, and the search results unranked box. Ta-da-da. Okay. So the way this one works, as always, we have my get functions and set functions that help me do your front end stuff here. And then we have all of this, right? So these, let's see, I might even do a little edit here. Finding the postings was the last thing we did. So now we have to do set the sorted stuff using the sort postings function that we're going to write, the intersect all function that we're going to write, and the get documents function. And within this one, we're actually going to have another function that's not, it's just a helper function. It's internal. We don't have it displayed out here anywhere. So we'll see it. So let's go. Yeah. So as usual, this is the basic idea. This is what your goal is. If you want to try to swing the bat on your own, you feel free. But from here on, we're going to, I'm going to do a walkthrough of how to implement this stuff. So we're going to take my complete file and we're going to throw it in the trash. And just to prove it's dead, well, oh no, it's broken. Oh no, none of it will work. Oh gosh, oh no. That's fine. So, as usual, we're going to take our syslib from last time and drop it in for next time. Now, if we reload, we'll get right about to the point that we last stopped at, right? So the indexing function's still doing its job. Even the query would you, right? So we get our query tokens just like last time, and we get our postings. Great. Let's skip with would you like, because that shows the sorting a little better. Okay, so next we need to start coding. So let me, of course, I always have my own notes, secret from you. I just want to do this more straightforward. So how do we start adding new information, right? So assign 4 functions, right? We'll have our new section here. Give ourselves a little white space, and let's get going. What are the names of our functions that we need? Here they are. So function sort postings. Oop, I put a space because I'm silly. Posts. We can call that anything, as always. We can give that anything. But the basic idea is we're going to feed this a nested list of postings, right? So an array of arrays of post values, like here, right? So this is an array at the highest level, and then it has its contents are smaller arrays, right? Small array, right? So this will be 3 arrays of postings from would you like in this particular example. So what this will do is it will come in and say, okay, I'm going to sort those arrays of postings within this top level array to put the smallest one first. To do that, we're actually going to use something called a lambda function. Now you don't need to, again, this is kind of like the regular expressions we used in other parts of our code demos. You don't need to fully understand them. I hope to give you a taste of understanding of them. So let's see here. We'll give this, so sort an array of posting. No, sorry. What's the best way to phrase this? Sort an array of postings arrays based on their length. Shortest to longest. Okay. So that's our goal. That's what this function is supposed to do. So, as usual, I like to set aside a variable sorted posts equals the posts, just in case we need to do some editing that we don't want to screw up an original value. You'll encounter that some other place in your coding career if you keep digging, but no worries for now. It's just kind of decent practice. So now we're going to use a function called sort, or rather a method of arrays called sort. So this is an array of arrays, right? So we're going to do this function, or this method called sorted posts. That's our variable full of all of our postings and stuff. And then we're going to do dot sort. Aha. So normally when you call sort, what it's going to do is it will actually, without like doing any assignment statements like these equal signs, it's actually just going to go ahead and change what's in this array. And it will sort it by some function that we use to detect which one goes on the left or the right? So when you're sorting, you have to have some criterion that determines whether or not how exactly you will be sorting. Now, in a lot of cases, you have a known function that will do this, right? You can sort based on a very specific function, but in this case, we need to define our own because we're trying to sort things based on properties that aren't sort of immediately available in the code. So what we're going to do is write a lambda function. So that's a weird thought. What the heck is a lambda function? I'm just going to separate this out a little bit so we can have a little bit more clear writing of this function. Remember that this is all still within the parentheses, so it's still, we're just passing a function to this sort method as a value. We're going to send it like, hey, sort. I'm going to write you a custom function right here and now in the middle of the code so that you can sort this the way I want you to. I know, it's kind of wild. This is a pretty strong power in a lot of programming languages to be able to throw functions around like that. It's good to get used to. So we're going to define a function. How do you write a lambda function? So function, and that's it. You tell it function x and y. Now, why would we do that? So this is a nameless function, you see. Normally, when we write a function, we give it a name, and then we start doing the arguments, right? In this case, we're just saying function. And that's shorthand for saying, oh, just define a function right here and now. Don't give it a name. Don't save it anywhere. Just throw it to the destination of the sort method that's going to go on. So we're giving it two values. A lambda function that you throw at a sort algorithm typically needs two values so that you can take two things and compare them, right? So what are we going to be comparing? Well, remember, kind of the goal is to be able to compare the length of two arrays, right? So this would be x for the purposes of sort, and this would be y. Okay, so now two different postings lists, two different postings arrays will be the arguments of this little lambda function that we're going to use to help sort. So we're going to define a function, right? Hooray. So we can do this with one line, and the idea is I need some value to determine if two things belong next to each other or not. And the easiest way to do that is we would say we're going to return some value, and that value will be x.length minus y.length. And that's it. That's it. So what are we getting at here? So what this is going to do now, sort is going to come in and say, okay, I'm going to look at each pair of items and do a sort. I'm going to figure it out. And it may do it in a more fancy way, like a bubble sort or something internally. But for your purposes, you can think of it in this linear fashion. So it's going to say, I have the postings for wood and I have the postings for like. So wood is going to be the x and like is going to be the y. So wood is 4 long. It has 4 postings, while like only has 2 postings. So 4 minus 2 is going to equal 2, right? Which to the function says, okay, this is actually top heavy. I need to put the first one needs to go on the right and the second one needs to go on the left, as opposed to the opposite case, whereas if it was negative, then it would do the reverse. That's all you really need to know. This is the fundamental idea behind the sorting, is that you have to give it some kind of value to judge which things need to be moved left and which things need to be moved right. Ultimately, now we have our postings sorted, so we can just go ahead and return those. Let's see if that does what I think it should do. Reload. Reload. Thank you. Didn't blow up. That's always nice. Let's look. Would you like? Okay. So we have, in the non-sorted ones, we have 4, 2, and then 6. In the sorted ones, we have 2, 4, 6. Hello. So now let's give it something that doesn't even exist. Buns. That's not in any of these. So that should be an empty list of postings. And once we get down here, aha, we have an empty list of postings. Fantastic. Okay. So our sorting function is working. Yay. What do we need to do next? Let me get this back to like. Okay. Oh, no. So next, what do we need? We need to write a function that is going to intersect all of these postings arrays, right? So find the common values between each and every one of them. We need one to do all of them, but before we do that, we need one to do just the basics. So we need an intersection function. Now, this is the one that we covered in the text. Oh boy, let's begin. So function intersect, by text I mean lecture. This is what we covered in lecture. So if we recall that algorithm, what did it do? What did it do in general? It took two sets, right? We'll call them sets, set A and set B, right? Lots of space. But we had a few components, right? We need pointers. We need valued pointers to say, I'm going to move, we're going to keep track of where we are in each list. In fact, let me do a quick trick. Go over to my website, go down to, when did we do this? Wildcard seems too late. Boolean queries? Our intersection algorithm, yes, okay. So this is our walkthrough. If you recall, what are the things that we need to do, right? We need a pointer to look at each value in the list, in the array. And we need to be able to increment them at certain times, right? So we're going to compare 1 and 3 in this little example. And then one, we're going to say no, and we're going to increment the smaller one, right? That'll move up. Is 3 and 2 the same? No. The smaller one moves up again. Are 3 and 3 the same? Yes. They'll both move up. That's the idea. So we need 2 pointers. You start at 0 because you start at the 0th position in any array. And pointer B will also be 0. Great. So, and then we will also keep a result, right? So we need to let a sort of a running result, that's an empty array, right? So as we look over here, we see that the result of this keeps acquiring new values. By the end of it, it has 3 and 6 in it. That's the same idea on the left here. So we have those variables set aside so we can use them. So now let's start implementing the algorithm, right? Well, wait, before I do so, let me get a little clearer. So pointers for array for comparing values in both arrays. Intermittent result. You should always write yourself comments. They're for you as well as anyone else who ever reads your code, but they're really for you, I promise. So, one moment. Consulting my notes, making things clear. So we're going to do a while loop. We haven't really messed with that much before, but it's another kind of loop. It's a value. The basic idea is while neither pointer has fallen off the end of its array. So while, right, two things. So while A is less than set A dot length, and so both of these must be true. we're only going to keep looping as long as both of these pointers are not yet at the end of the array. And b is less than set b dot length, right? So, aha. So what will we do the whole time that we iterate over this? Well, we will do some things. We're going to compare the values in each of these, and depending on what we find, we will either add this to our array or we'll increment our value. So we'll add it to the result array, or we will increment our pointers, or both often. So first question is, if the values match, right? Make sure to indent, give yourself clarity. Clarity's key. So if the values do match, what do? Well, we're going to add the value to the array. That's one thing. So how do we do this? If parse int set a pointer a. Oof, that's a little dense. Let's talk about that. I'm doing parse int because all of our values are stored in strings, if you look at them, typically. So for comparisons, it makes it a little easier, more consistent to make sure you're doing parsing ints. So if the value in set a at position pointer a, right, is equal to parse int of the value in set b at position b, that's our if statement. So if that's true, what does that mean? That means the values match. So if this equals this results in true, then yeah, do this part. What do we do when the values match? Well, grab the answer into our result, and that will be by saying res.push. And we can pick either one. Set a sub a is fine, right? Because they're the same. In this case, we know they're the same because that happened in our if statement. So grab the answer into our result, and then also increment both pointers, right? Because we've already figured out that these match, and we know that these values are all unique values. We're never going to see them again. We can increment both of them forward. So looking back at the example, when we find a match, hey, we're good. We know that 3 is never going to match anything higher than 3 in both cases, so we just move on to 6 and 5. Now we know that won't match, but we'll figure that out later. So we increment both pointers. You can increment things in a few ways. The easiest is a++ and b++. Really, that's all you do. This is an operator that changes the value in a to 1 more than it was. So we start at 0, and hey, we found a match, bump them both up 1. Cool. So that's our first case. If the values match, do this. Else, and we can give ourselves a note here, if they don't match, right? So either they will match or they won't match. That's it. Then we have a couple of different things to do. We can either increment a or b. Remember what we're doing here, the way this is all streamlined is that we will increment a if the value is lower, right? So if the value so they don't match, right? And the idea is, which one are we going to increment? We can't increment 3 in this first case because we're not sure if we're going to run into a 3. If I increment from 3 now, I'll never find the match on the other list. So we can only increment the lower one if we want to make sure to hit all the possible combinations. So we need to check which one's larger. So if they don't match, if pointer A's value is smaller, advance pointer A. So how do we check that? If, again, parse int set a sub a is less than parse int set b sub b. Okay. Let's pick that apart. I just typed it. So again, parsing ints just to make sure they're in numerical form. So the value in A, so we already know they don't match. So if A is less than B, then what do? We increment A. And that's it. We don't add anything to our array because this is not a match. We're just trying to move forward efficiently. So that's the first case. The next case is going to be else, right? Otherwise, B must be larger, or sorry, smaller, because let's rule that out. So we know they didn't match, right? And we also know that in this case, in this final else case, well, A is not smaller, A must be larger, so B must be smaller. Then we will increment B. It's a logical puzzle. These are the things you often run into in programming. So that's the while loop. We keep going, keep going, keep going. Eventually, A or B is going to fall off the end of its list, right? Pump, 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 pump. We get finally to 6 and 8. Hey, do they match? No. So increment the smaller one, 6 falls off. Aha! We've tripped our trap on the while loop, and now we break out. So the idea is that this result is accumulating, just like in this visual down here. This result accumulates values based on what's happening in the while loop. And at the end, we break out, and we will return what's in the result. So return res. Now, trouble right now is it's harder to test this because we don't have an outward-facing piece, right? We need to then run through and do the pair-by-pair intersections to get this. So let's look at just how it works. Let's make sure it works the way we hope. Oh, no. Oh, that's fine. That's intersect all is not defined. Don't worry about that. So intersect. What's our example? We had 1, 3, 5, 9, and we had 2, 3, 7, 9. Now, when I close this, what should we see? What do we expect to see? 1 don't match, 2, 3s are there, 9s are there. Does it work? Hey, our algorithm has done it. Let's change a couple things just to make sure. 5, great. And then we'll make this one a 2 to make sure they all match. Great. The intersection algorithm is working. And you can know in your heart of hearts, the way that we talked about this before, this is the most efficient way to do this. It is linear time. So take 2 sets and find their intersecting members, right? Cool. So now we have our intersect tool written. The cool thing about this tool is that it's not custom written just to do, just postings. This works on any arrays with values in them that can be compared. So this intersection algorithm, good. Keep going. You can use it. It won't always be perfectly efficient unless they're sorted, so let's actually write ourselves a note. Most efficient. No, actually, it only works with sets sorted in ascending order. Little warning note. So that is our intersection algorithm. Ta-da! What's next? We now need to do the intersect all algorithm. So again, consult my notes. It's okay, I wrote them. I earned them. So, all right. Finally, for this intersection component, we're going to write another function, right? That's going to use this intersect function. So function, intersect all. And what do we need to intersect? What are we looking for? We're going to, We're going to run the intersection algorithm on the sorted lists of the sorted list of sorted postings lists, right? So the thing we took the trouble to sort by the length of the list beforehand. So we'll just call that terms postings. Just try to give ourselves a sort of a clear name. But of course, as I always do, my own quirk, but not bad practice. Okay, so we're gonna grab those out and see what we can do with them. Remember, our note is intersect each pair of postings and the intermittent results until there are either no postings left or no more lists to postings arrays to process, right? The idea being that we're going to go through each list of postings for each query token that we get out of our index, and we're going to compare them two at a time. So let's do this. First, the simplest way to do this is just break off the first one into our intermittent results. So as before, we're going to have res, some kind of result bucket. And we can use a cool function for this called shift. So what are we trying to do? Pull out the first set of postings to be compared, right? And then we will run through the rest of the list and intersect this result with each one going forward. Now, before we muck around with that, let me show you what shift does. So let's say var x is 1, 2, 3, 4, 5, 6, right? X.shift does two things. It returns 1, which is the first value. But if we look inside x now, 1 is missing. So it did two things at once. It returned the value and got rid of it from the array. It broke it off, right? When we use that here, we'll say post.shift, right? And what that does is it says, okay, we're going to take the first array of postings and we're going to put them in this res. We're also going to delete them from the posts value, right? So we will remove them. Let's show that more clearly. So var y is, let's say we got postings 1, 2, 3, 4 and 5, and 6, 7, 8. This is a nested array, just like our postings will be. So that's y, right? Y. Look at y. Neat. We have 3 arrays, different sizes. Cool, cool, cool. So if I call shift on y, let's say var z equals shift, or y.shift, what do you think will happen? What goes into z and what remains in y? Well, if we look at z, it has the 1, 2, 3 array. And if we look at y, aha, it's still 2 arrays. We've snapped off the front. So that's just to make it a little bit simpler going forward. Now we can program just to say, okay, so if this first one is the intermediate results, and remember, it's also the smallest result, then that means we're able to just continue forward until we run out of lists. So next set of logic. So a couple things. As long as first, our results list is not empty, meaning we don't want to keep running through this list, or through this list of possible values if we have nothing in the result, right? So if I've already, so because intersection is always reductive, you will always lose information. You can't add information, because if something's in one of your postings lists and not in the other one, it will never get added, right? We're always reducing the possibilities. So if our list becomes empty, our result list becomes empty, that means, hey, this thing that we're looking for, the query that you're looking for, does not exist in the collection. We can break out. So that's our first fail condition. And then our second one is the arrays of postings, or sorry, wait, the array of postings arrays left to process is also not empty. Okay, so I use these interchangeably because of some programming mucking around I do. Array is the technical term for the structure that we're talking about. I just say list because it kind of makes sense too, right? This is a list of values. It's also an array of values, right? If you get deeper into programming, you will need to know the difference between those things. But for now, just think of them in the same loose association. So this is a while loop, right? We're going to do the same thing over and over. We're going to intersect the result with the next set of postings, intersect the result, next set of postings, over and over and over until we run dry. So how do we define what running dry is? So while loop, again, our old friend. So what are these two things? Res dot length, right? We want to make sure our result list is not empty. Does not equal 0. And what was the other one? Oh, yeah. Posts dot length does not equal 0, right? Okay, let's recap that. So while the length of our result isn't 0, we haven't eliminated this possible search entirely, as in there are no postings that match any of this criteria, right? So as long as that's not true, and as long as we still have something left to process in our list of postings like this, then we can proceed, right? And how do we proceed? Well, we say res. We're going to reassign res, right? Because we want the res value to hold our intermittent results, right? That keep changing over time. So res is, we want to have the value of the intersection, which we intersect is the name of our function that we wrote just up above, and we verified that it worked. So intersect res with post.shift again. We're doing some funny stuff here, kind of fun stuff too. We're using the same two ideas, right? We're going to snap off the end, or the first value of our postings, plop it into res. Then each time we need to intersect, we're going to snap off another value, and it will keep shrinking, right? Until post.length is 0 or res.length is 0. This ought to work. So let's do it. Return res. Ooh, moment of truth. It's possible I've made a terrible typo or a logical error. Who knows? Let's find out. Let's save and let's reload this biz. Nothing broken yet. Looks okay. Let's see. Would you? Hey, 0 and 3. If we add like, that shouldn't change it, right? 0 and 3. What about I would? Aha. So I appears in several places. I appears in 4 of them. Would appears in 4 of them. But we know that they only appear together in 2 of them. I would not and I would not. 4 and 5. Fantastic. So, what about I would buns? That should not appear anywhere because the word buns does not appear. This would be one of those Google results that says, hey, did you mean something else? Because this returned nothing in our collection, right? So, great. We're getting there. We're almost done. We have now found a way to process a user query into the postings of where that query exists in the text. Great. So let's do our last function. What is it? Well, we don't want to just dump postings at our user. We want to get documents for them to actually look at, right? So the last thing on our list is the getDocuments function. This one's fairly straightforward. Postings, but we're going to also need to go grab our collection, right? And as I've already made work for you in this particular page, when I call this function, your function, I say, hey, I want to set the final value of unranked, this search result, to get the documents, take our intersected Q posts, and then get our collection as well, right? So the collection is stored up here. That's why I separated it out, so that we can go grab values out of it. So let's do it. It's fairly straightforward. Compared to all the complex stuff we've just been doing, this one's nice and simple. So retrieve documents from the collection based on the postings. Well, let's see, but based on the intersected list of postings, right? So, how do we do? As usual, let result equal 0. In this case, we're not actually changing anything, so I don't set aside an extra variable here to keep track of things that we might delete. So result is, as usual, we want result. In fact, we'll keep it consistent as the last one's res, right? So the result in this case is going to be a list of the document text, right? An array of document text. So we start with an empty array, and now what are we going to do? We're going to run through all of our postings that we pulled in. So for, and if you remember, P, so postings, so we'll call it post of postings, right? So what does post have in it? It has a single numerical value. Remember, so would you. At the end here, we have 0 and we have 3. Now, thankfully in JavaScript, you don't really have to screw around too much when you're indexing into an array. You can use the actual text-based version. Not best practice, but we're going to just keep it simple that way. So for each posting in this list of postings that we've calculated finally, we're going to go grab, we're going to say res.push. As always, we like to push things into this array. Into this array. So we're going to add something to this array, and what we're going to do is we're going to do whatever is in collection at index of our posting. Oop. So what does this do? For each posting, go grab its document and add it to the array of resulting. Oop. From our search overall. So now by the end of this loop, res should contain the text of all of our documents. So we can return res. Okay. Reload it. Reload it. Reload it. Good sign. Real quick, check. Look at the console, no errors. Hey, let's see if it blows up. Would you like... Where does this appear? If we remember, it should be in lines 0 and 3. Would you like green eggs and ham? Line 0. Would you like them here or there? Line 3, the fourth one. Fantastic. So, that's it. This is the full breakdown of retrieving Boolean search results, right? We still haven't ranked them, but we have retrieved results from the document for use. Real quick, let me see if I can grab, what's a text document I can snatch? I just wanted to try something bigger, but you get the idea, I think. Yeah, so you can feed, try yourself, try feeding anything else into here. You could do, in fact, I have somewhere. We're going to go to a little secret space. Shh, it's a secret. Great. Let's snag, you know what I have in here? I have the full Constitution. So let's see what this search engine does with the full Constitution. It's going to be a little upset because it's going to be loading a lot of stuff. But hey, look at this collection. It's getting there. We have it separated into articles. And would you like, I'm going to guess, probably does not occur. Would, you doesn't, and like. So maybe what about just would like? Still nothing intersects. Okay. What about we the people? Where does that occur in our, aha, just the first line. You learned something today. Great. So yeah, that's the idea. This is how you build a search engine, right? There's obviously more steps, but we have touched on the core ideas. And there's a lot of content in here. Don't worry about it. This is a way to search. But look at our index. Oh my gosh, so much going on. So much going on. And yet it still works. You can find specific passages that have information. What about judiciary? Nowhere. Judicial. Hey, there's a few. That's just a single term. What about power? Judicial power. Slightly smaller. Huh. Great. Anyway, so that's the idea. As usual, your goal is to write these functions, and again, you can write them exactly as I've written them, and it should do it. Just you have to do it, right? So, and this works. So this is your so far Boolean search system. Future assignments will include the ability to start ranking them and doing all the front end lifting. But for now, this is a fully functional Boolean search system. Congratulations. Okay, that's it. Take care. Have a nice one.